So let's get started. All right, welcome to the last session of the workshop. Well, guess what? It is the 8th session, so you've gone through 7 sessions of what turned out to be 2 hours each. Yeah, so much for me saying it's probably going to be 90 minutes each session. Yeah, it never happened that way. But at least you've hopefully been enjoying it. This is the last one, and I still have a bit to teach you. All right, so we'll talk and cover this topic of, let me put it in presentation mode. Yeah, it's working out. On the code, data organization, and going beyond this workshop. All right, so diving in, tracking your analysis code is critical. So hopefully by now, this makes sense to you, or at least you can agree with me partially on this. That when it comes to truly making sense of your work, for example, for the sake of reproducible research or making sense of others' work, it's important that you actually share the code that went into analysis, right? Like when two people talk about what they think are the two in the same analysis, it might not be the case that you guys actually have a completely same idea of what the analysis means. Oftentimes, you actually have to dig through and read the code to be fairly sure what actually went. There might be a couple of tricks and stuff they threw in, maybe additional assumptions that actually matters for the results. And so this is the way. So if you really share each other with the code, this actually allows others to work off of your code, and you could do the same on others as well. Like by them sharing the code, you don't have to repeat their work. You don't have to guess as much about what's going on. And if they already implemented a fairly sophisticated algorithm, you can already take advantage of it. And so another way to think about sharing code with others is that this is a nice way for others to check your code for free. There's even exists online services where you pay money for someone to check your code for integrity and whatnot. So if you think about it, this is a free way to get that check. And of course, it might be the case that if you make it publicly accessible, that people might actually contribute back to your project and improve things for you. I mean, obviously, you probably want to check and make sure that what they think is an improvement in appropriate change is actually an appropriate change in your mind. But it's a good way to start building up code resources. So, if I ask you the question, what's the best way to organize, track, and share your code? And I hope by now you should know the answer. Yeah, Git and GitHub, right? So if you use Git and GitHub to organize, track, and share your code, it lets you keep your files stay organized in the sense that you can track multiple versions as you make changes, you make commits. And although we haven't exactly covered how would it be that you go back and commit, so at least you should be rest assured that you can. Because you have actual commits that represents different stages of your code, there are ways to go back to it. If you just Google for Git, revert commit or something like that, there are short commands that comes up for you to be able to go back in history. And this really takes away the need for something that people would commonly do otherwise, like duplication of their code. They will copy and paste an entire folder just because they want to make some changes, but without causing a disaster in case they wanted to go back. If you actually do this approach, your folder will be soon filled with a bunch of copies, and then you will lose track of what is what. And you don't really have to do this if you use a system like Git, because you can create something called branches, which lets you quickly try out different changes and keep on making commits. But later on, if you decide none of that actually is something you want to keep, it just was not worth, or you don't actually want to keep it anymore, you can simply switch back to the main original branch and pretend like nothing happened. Also, by having Git and GitHub combined, this allows you to efficiently share your code with others. So we've already seen how I, for example, shared a code base for the whole workshop by using GitHub. And you guys actually can navigate and look at the code, and even better, actually make a fork off of it and start working on it as your own copy. And even with the potential of making some commit changes and contribution back to the repository, should you decide using the workflow pull requests. So all in all, you should be thinking, okay, Git and GitHub is your solution for code management and sharing. This is fairly well established. This is by far the standard for the open source community when it comes to code sharing. So this is pretty good, well tested, it behaves well. This should be your solution. And then by now, through the workshop, I hope that you have gained some familiarity, if anything, so that Git and GitHub no longer sounds extremely scary. Okay, but the problem is, or at least one thing to keep in mind, is that research is not just going to be about your code, right? It actually has a lot to do with your data. A code wouldn't mean much if you don't have data on which you can perform your analysis. So obviously you also want to, just like you want to organize and share data, share the code, you probably also want to think about organizing and eventually sharing your data if it comes, for example, in the sake of maybe publishing and then eventually sharing data that goes along with your publication. Now there's a lot of pressure from funding agents like NIH to make sure that at the end of the day, your code and data are published and shared so others can reproduce your research results. But it turns out keeping your data organized is difficult. So for those of you who have already been dealing with this, you probably know what I mean. It's actually not that easy to just say, oh, let's just keep your data organized. It's not like that. It takes far more effort than that. And when two or more people work on two or different data sets, they all have different ideas of what an organization means. And something that looks organized for one may not be exactly organized for others. So at least there'd be difficulty communicating what each data means. So just sharing the raw recording is also often not enough. So if I record, say, a spike trace from a brain, and I say I'm going to make my data available and just give you this raw trace dump, you probably have no idea what this was about. You have no idea what kind of mouse or what kind of animal it was even about. What was the stimulus? Was there even a stimulus? What kind of recording apparatus? Where is this recorded from? V1, LM, PFC? Maybe data is not going to be enough to tell you that. So there are a lot of information that goes on top of the raw data that is actually crucial to describe and really understand your data. So this can go something along the line of subjects. What are the stimulus you've shown? What are the recording apparatus you use? What are the ways by which you organize your recording sessions? What are the trial means? All of these information become critical when you try to understand data and analyze it. And this implicitly happens in your brain. But when it comes time to share, you have to transfer that knowledge as well. And this is oftentimes one missing thing, especially in the field of neuroscience, is how do you really share data in a way that each other can actually understand and make use of the data you just put online. So, and then on top of it, when it comes to like organizing data, it's often forgotten that the parameters and all sorts of configuration and knobs you turn when you do your analysis are also data. Right? That exact hyperparameters, that exact weights, all the choices that went into for your analysis is as crucial as the original data to actually reproduce your results or to actually even understand what you just did. So things like that can easily be forgotten when it comes to time to share the data. So this is where I get to introduce you this one package called Data Joint. And I think this is typically where I should put some sort of disclaimer because I'm actually one of the co-authors of Data Joint. So this is a package me and Dmitry Utsenko from our lab developed. So he developed it first in MATLAB, and I came and we developed it together further into a Python version, and ever since we've been maintaining it. All right, so what's Data Joint? So Data Joint is a library. So I'm going to start using the term library to mean something like packages. Library is a more generic term that goes beyond necessarily Python, just collection of code effectively. For Python and MATLAB, for the purpose of creating, organizing, and running a data pipeline. And I'll go into the details, but data pipeline is essentially something that captures the entire flow of data, starting with the acquisition, or even before that, starting with the very entry of mouse on which you are going to perform acquisition. Acquired data gets into the data pipeline, pre-processing goes into the data pipeline, and any subsequent analysis step, all the way up to and including figure generation for your very own manuscript, is going to be considered a part of your data pipeline. So, but before we go too much into this, we need to actually give you data join package. So that means you have to install the data join package, and this is where I get to discuss what does it mean to install packages in Python. You already seen a glimpse of it when you install the PyTorch package, or at least those of you who've installed the PyTorch package, you've got to try a bit of this. But there are two major tools that exist currently. There are actually others, but the major ones you probably want to be aware for Python package installation are pip and conda. So pip first. Pip is an official Python tool for package installation and package distribution. So official in the sense that it is the same Python open source community that's behind pip. And what it does by default is it discovers and basically searches and then installs Python packages that are registered with a particular website inventory, essentially called Python Package Index or PyPI. And you can actually take a look at them by visiting pypi.org. And the command is going to go along the line of pip install something. So if you say pip install package name, assuming that the package actually exists in the PyPI, the Python package index, it will grab that, download it, and then install the package for you so you can use it from wherever you are using Python. So that's the Python package indexing, the associated pip installer. All right, the alternative is Conda. So Conda is yet another Python package management tool that's provided as part of an Anaconda distribution. So for this whole workshop, you guys installed an Anaconda distribution. Conda comes with it. And just like pip was for PyPI, Conda is for Anaconda managed packages. So by default, it discovers and tows Python packages that are registered with Anaconda. So it means it actually searches and grabs packages from different locations than what PyPI manages and maintains. And the installation command actually looks fairly similar. If you just replace Conda with pip with Conda, you pretty much get it. It's Conda install package name. But again, the package name will be searched from the Conda inventory. And you can actually go ahead and take a look at this link, and you will see all the listing of Anaconda managed packages. I'll be sharing these slides, so you can also just explore it later. So you might be wondering, why are there two or even more? Why are there more than one? Like, why couldn't they just decide and just stick with one package manager? Well, it's one reason, at least the argument for it, is that Conda actually does a bit more than pip in that it actually knows a bit more about your system. So whereas pip only installs really pure Python-based stuff, or Python and slightly C-based packages, but really doesn't install anything extra for you. So there are many other libraries, for example, written in C and C++ that you have to maybe install for being able to handle videos or being able to work with GPUs. There are these extra libraries that's not considered part of a Python package, but still your package can ultimately depend on. If you were to use pip, you have to install these dependencies yourself and then finally use pip. Whereas Conda, they actually have ability to go a bit further and manipulate your system so that if you say Conda install, it can go ahead and install these third-party libraries outside of Python. So that's one reason for which if you have a library that has a heavy dependence on external C++ libraries, you might be better off using Conda because they often take care of everything, not just the Python code itself, but things it depends on. But that being said, pip is still the official Python package management system. And given its simplicity, it is by far the most common place for people to upload their package and make their work available. So you will find far more packages available through PyPI and therefore pip compared to the Conda. So you might be asking, okay, which one should you use? Well, just like many things in life, there's no right answer to this, right? Oftentimes, the package developer will actually have a recommendation on it. So if you have a package you're interested in, if you go to their web page, maybe they have a dedicated website or maybe it's just a GitHub page, they often tell you what is the best way to install their package. And some will recommend to use Conda, some will just tell you to use pip. And some packages are actually only available on PyPI, therefore pip, as I said, because of the simplicity. And oftentimes if a developer is pressured to make a decision between one of those two, it's almost no-brainer you will definitely go for pip. Conda is usually considered an addition on top because pip is the one that's by far the most popular, but Conda is a bit more advanced. So if you were to provide one place, people will go for pip. And as I said, so pip is still considered a standard. So most of the time you'll find more packages in pip, but because of its kind of restriction on what it can really do on your system, sometimes you'll find much easier to install using Conda, especially if the library depends on something else. So that being said, DataJoin is actually available on both, but you actually get more updated version if you use pip. So with that, let's go ahead and install DataJoin. What you do is open up a terminal if you're on Mac OS, open up an Anaconda prompt if you're on Windows, and simply run the command pip install DataJoin. It might take some time to run, so just let it run.
You don't have to worry about where it installs, right?
That's automatically managed by your system. So the trick behind this actually is that because you guys all install Anaconda distribution, which comes with Conda, it actually also comes with pip. At the end of the day, the packages are nothing but folders with a bunch of Python code in it. So whether you use whether you use conda to install it or whether you use pip to install, they all go into some pre-designated location that Anaconda decided, and it all just gets there. It's just that how you really get the package there and make sure all the libraries it depends on configure depends on whether it's conda installation or pip installation.
I'm sorry, this is interesting. Non-existing installation of network X 2.1.
Okay, and then did it error out or?
Yeah, it uninstalled it and then successfully installed something.
Okay, cool. Yeah, so it just updated with the newer version. So this, I'm not going to actually linger too much. The reason I didn't actually put this forward as a thing you have to do for this session is because I'm going to actually keep the data join demonstration and following along to be more or less optional for you guys. One of the reasons being there are actually extensive tutorials for data join that I wrote that you actually can go online and follow it through, and there I put much more step-by-step instructions. And furthermore, on top, I've actually given recently 2 days workshop on data join with all the videos and code sources. So if you're really interested in this, on top of being able to talk to me about it, you can just go ahead and follow through the tutorials and the workshop material. So for that reason, and it's much more detailed. I actually spend much more time covering every aspect of data join. So if you're interested, that's where you can actually learn further about it. So today I'm going to keep a more or less high-level overview where I'll step through some of the features of data join to show you what it can do, but you don't have to worry too much about like running in front of you. That being said, if you want to run, by all means, please. You're given all the necessary material that you should be able to do so. Okay, you guys all good? More or less installed. I'm just going to go ahead. Okay, so one caveat or one thing to be aware with the data join, and as I'm going to mention, is the data join actually works with the database service behind the scenes. So the idea behind data join is that you manage and organize your data into data pipeline, which actually is hosted on the database service. Now that might sound pretty complicated, but that just means some piece of software that's called database server. And you could actually run on your laptop, you could run on desktop in your lab, or you could actually be running on the cloud. And in fact, what you can do is if you go to datajoin.io, the website, we have a free sign up for an account, a tutorial database account. That if you go sign up, you actually get an email with the username and password that you can use to just interact with the database and test things out. So I sent this information out in the Slack message. If you had a chance to do it and you already have a username and password, good. If you don't, you could still go and try and quickly sign up. But if not, then just sit back and relax and just watch me do these things. You can all follow this after the fact. All right, so let's get back to the topic of what is data join, because I do want to cover this a bit. So I already mentioned data join is about developing data pipeline, and data pipeline is something that captures entire flow of data from data entry all the way up to pre-processing and analysis, and maybe even up to figure generation. That's probably still vague, so another take on it is like this question, what is a data pipeline again? And you could go, for example, to data join documentation and read a line that describes what a data pipeline is. And the definition there at the current point stands and says, a data pipeline is a sequence of steps, more generally a directed acyclic graph with integrated storage at each step. These steps may be thought of as nodes in the graph. So this probably leaves you wondering what that means, right? Now, probably not the most clearest or succinct definition. It is true. So once you know it, that's completely an accurate description of what a data pipeline is. But I would like to give you a bit more of like intuitive view on what it means. So data pipeline is really about things in your experiments. And what I mean by things are, for example, you work with mouse. We might work with multiple of them, so you have mice. Each of them say identified by some ID. You work with sessions, right? So you go in and perform some experiments. So you have a concept of experiment sessions that you perform on day in, day out. And you probably work with neurons, being a neuroscientist. At least to some degree, you work with neurons. And once in a while, because you analyze these things, you might be interested in statistics you compute. Statistics is yet another thing that you're interested in computing and perhaps keeping track across your experiments. You probably have a couple parameters for your analysis, which actually is involved in performing analysis or like processing such as in spike detection, where you detect and keep track of spikes. So these are all things, or often also known as, referred to as entities in data join lingo, These are things that you think of, and when you actually talk to other experimenters or just researchers in general, you think and talk in terms of these nouns or things about your experiment. Even though you might be thinking about the algorithm for, say, like how to detect spikes, most of the time you are focused on how to get to spikes. You're not so concerned about the exact Monte Carlo-based method approximation that really gets you to spikes. Some of us would be very thrilled with that discussion, but ultimately most of the time these analysis and processings are means to go from one thing to another. So data pipeline lets you organize these into sequences into a one flow diagram. And it captures relationships or dependencies between the things in your project, and this gives you the benefit of integrity check, as we'll actually take a look at. So here, just quickly, you can see that there's mouse at the very beginning. So you enter some information about the mouse you're going to work on. Every experimental session is about a mouse, so a session depends on the mouse. And every session, you can actually record multiple neurons. So neuron actually is dependent on a session. And then furthermore, some statistics you compute could be about the neuron you recorded. You can also detect spikes about the neuron you record. So these are all capturing what kind of things you are recording, acquiring, or computing, and how do they relate to each other. This is really all there is to data pipeline. And more or less really actually ends up reflecting what's going on in your mind, but maybe not just laid out like this most of the time. Okay, so again, each thing is represented as a table and data joint. So this is the part. So once you actually put the things into your pipeline, we ultimately keep track of each of these things as a simple table. And each entry in the table ends up representing one instance of a thing, as we quickly see. So here, just to motivate this further, I want to give a somewhat concrete example. So let's try to think about the scenario for how you might want to go build a pipeline for a hypothetical scenario of an experiment. So let's say your lab houses many, many mice, and each mouse is identified by a unique ID. Every time they're born, they're assigned an ID. Maybe you ear tag them to make sure there's association with an ID per mouse. Now, per mouse, you don't want to only know its ID. You do want to keep track of important information. For example, their date of birth and their sex. Those information matter, so you do want to keep track of those somewhere in your system. Now, as a hardworking neuroscientist, you're going to perform experiments every single day. And you might even work with multiple mice in a course of a day. Let's say because of the way maybe your very experiment makes your mouse extremely tired, per day you work with one mouse for one session only. Like you wouldn't use one mouse across multiple sessions within a day. Let's just assume that's how you're going to run this experiment. Now for each experimental session, you would like to record from mouse. So you would like to record what mouse you work with. I mean, you obviously have to know what is the mouse you're actually performing an experiment on. And also when you perform the experiment, because things like that is how you keep track. So otherwise, this might be something you find in your lab notebook. Now, a couple other information you might want to also keep track is like maybe in your lab there are different experimental setups, so you would like to also know which setup this experiment was performed on. Maybe down the line you actually figure out there's an issue with one of the setups. You would like to be able to go back and figure out which session's been performed on that particular setup. Now, in each experimental session, what you do is you record electrical activity from a single neuron. So maybe you actually do is lower the electrode, or you might actually do a patch experiment where you record from a single neuron an electrical activity. Your recording system, some sort of machinery that's probably put together, or maybe you put together, has a way of organizing this such that at the end of a recording session, it produces a single data file, which is a raw data trace for the neuronal activity. Ultimately speaking, you down the line will like to work with these raw data traces and convert them into spikes. You want to detect spikes and perform additional analysis. So say this is not obviously a complete picture. I haven't really explained what an experiment is about, what is the hypothesis, what are the stimulus, but you could imagine this could be fairly typical scenario for electrophysiological lab. You don't have to be stuck with this. You could easily change the subject mouse with monkey or maybe human if you work with human subjects. You're not going to quite do a single lecture recording in human, I bet, but you're probably going to do some other forms of recordings. You again still want to have a concept of a session. Maybe a session is when a subject walks in, you perform some psychophysics session, and recording would be their responses. In that case, maybe there are finer ways by which you want to subdivide, say, into trials. But these are all the things that goes into thinking about what are the things involved. Now, after going through the sentence, one thing you could do is highlight the important nouns or things that you find in an experiment. So here, I have placed my biased view of what are the important things. You notice that I didn't highlight every single noun. There's a bit of selection criteria going on. But essentially, you have mouse or mice that you want to keep track of. You work with them. There's some information about mice that you want to keep track of, like ID, its sex, its birth date. You also have experimental session. Now notice experiment session is nothing concrete. You cannot toss and throw around experimental session, but definitely something you think about in your mind. It's a thing, right? So you have an experimental session. An experiment session is going to be about a mouse and about the date on which this session was performed. And maybe about some extra information like which experimental setup when the session was performed on. And finally, down the line, you actually probably want to do recording. So you actually have recording for neurons that you record. And then maybe even further down, you want to perform analysis and detect spikes. So spikes are yet another thing you want to represent. So a couple of things we already identified are mouse, experiment session, neurons, and spikes. So what we're going to do now is take these and try to represent them as part of the data pipeline in DataJoint. So let's just start thinking about a mouse first. You want to represent all the information about mouse. You want to keep track of it. So the first question you should ask when you're encountering stuff like this is, how can I uniquely identify a single mice or single mouse? So there's been a lot of hints. A lot of hints exist already in the picture. So yes, it's a mouse ID. So you can say that if you know the mouse ID, you can uniquely identify the mouse. I mean, that's what you guarantee yourself. I mean, I hope that some system like that exists in every single lab that works with animal, right? You want to be able to uniquely identify. Sometimes your confidence in the face matching system of mouse is probably not the most comfortable one, right? So hopefully every mouse has some ID, and therefore, minimally speaking, a simplest table like this where it's only one column of mouse ID can still have separate rows that represents one mouse. Now obviously that's not going to be quite enough, but let's start with this. So here, the column that really uniquely identifies your entry or row, which is about mouse, so in each entry would be mouse, the one that uniquely identifies it will be called a primary key. And every row here is a mouse, because this is a mouse table. Now you also want to keep track of additional information about the mouse. So we already said we want to keep track of its date of birth and sex. But notice that there's only one column for primary key here because that's all it takes to really uniquely identify a single mouse, and every other information is really associated information. Okay, so far so clear? So this is how we go about mouse. Okay, so now we kind of introduced you to where we're heading in terms of the data. Let's actually switch gears and look at the notebook and actually look at how you would build these things inside DataJoint. So I'm going to exit at this point. I actually have to open it. So, I mean, as usual, if you just go to the repository and if you perform git pull upstream master to get the latest of the notebook, you should be able to get it. I already have done it, so I already have everything updated. And now if you launch Jupyter Lab, it will open up the most, by now, very common, and you've seen this interface a lot. Okay, so I'm just getting in. So as I said, if you don't have the username and password, because if you already signed up and got a username and password from datajoin.io, cool, you can actually follow along and enter the information and actually write the code yourself. But if that's not the case, don't worry, just sit back and relax and just watch me do it. Okay, so now we get to actually see DataJoint in action. Just like many other packages, we will go ahead and import it. But as always, first thing first, let's go ahead and import packages we know we're going to use pretty much every single time you open up the notebook, which are your NumPy and Matplotlib. As I said, this kind of should be your second nature. Right? There's almost no time that you don't need this for. At least if you import it, it's nice and you don't really have to worry about it later. Now, just like matplotlib and numpy, when you want to use the package data join, you just go ahead and import it. There's no difference. Just because it's something created by me doesn't suddenly make it back differently. You just have to import the package. The convention of importing data join is to import as DJ. So you just say import data join as DJ. And here I'm also importing another package called getPass. This is actually a utility to be able to enter password into your thing without showing all your passwords out. So I'll show you what it means very shortly. The reason I have to do that, or at least in my sense of security, is that I'm about to enter information for how to connect to the database. So when you actually use data join, the first thing you have to do is tell them enough information so they know which database to connect to and what's the username and password to use. So if you sign up with datajoin.io, you have to set the database.host configuration to tutorial-db-datajoin.io, so which should be something that's already typed there for you. If you're going to follow along with me, you have to make sure you replace the user portion to be the username you picked during the sign-up process. So for me, it's EY Walker. Unless you're me, you don't have EY Walker, so you should use your own username. And on top, you have to type the password. For me, since I'm up here showing it, I just decided to take extra precaution and not reveal my password, although this is not the most critical password. So if you use getPass, it's like input. If you remember input where you can tell the text, it would prompt and it will return. Except the input when you're typing, it shows exactly what you type. With getPass, it puts stars just like any appropriate password prompter should. So I run it, it asks for my password, and I enter it. And now I just get to connect just to make sure I can connect. And here it didn't error out when I say DJ con. This suggests that my connection was successful, my credentials are correct. So if you're trying this along, like try to get to this stage. If it doesn't work, then maybe your password is not right, or just verify a couple of things. But again, if you're having difficulty, don't stress over too much. You can just learn as much today by following me through here. So we already discussed data pipeline. I put this information here in case you were ignoring what I said in the last 10 to 15 minutes. Happens once in a while. So here I already mentioned like the mouse ID exists, and there are additional information you want to keep track of. Mouse ID is your primary key because that uniquely identifies your mouse. Okay, so what's more, the fun part is we actually get to create this table. We so far only talk about tables and being the pipeline and stuff, but we're not really creating it. We now actually get to create it. Before we get to create, though, we have to define something called schema. Schema is kind of like a folder where you basically get to take all the tables and put it under one collection so they have one nice place to live. So oftentimes you just give schema some meaningful name. In this case, there's a bit of code involved here because if you sign up through our datajoin.io, you actually get special permission that you can create any schema that starts with your username followed by an underscore. Anything beyond that, you have no control whatsoever. This is how we make sure that your schema gets separated from me. I have no control over your schema. You have no control over my schema unless explicitly share it with you. So here, this is just a trick to say, take the username, replace it before the underscore. So this way you actually get username under underscore pipeline. So that's what I get to create. So this just creates a schema. You can just look at the schema again. So in my case, it's EY Walker underscore pipeline because my username is EY Walker. Okay. All right. So that being said, the way you define tables in DataJoin is by defining classes. So just like we talk about classes is how you define, say, a new module, new neural network in PyTorch, here we also take advantage of classes to define a new table. And just like there, you inherit it from NN module to get all the extra baggage of tricks and methods and properties that already comes with it. You do the same, you inherit from dj.manual. I'm not going to step too much detail into this, but the idea here is that you define a class, you put an add schema on top. This means that put this table in the schema we just created. I'm using a lot of Python tricks that we haven't quite covered, so just kind of generally take it. And then there's a particular property I'm defining called definition, which actually has a specific syntax to define what goes into my table. So you see that I basically have a comment. And then following that, I basically have an entry called mouse ID. I'm saying this is going to be an integer. And I have additional comments saying this is going to be a unique animal ID. I separate it by dash, dash, dash to indicate what's above is my primary key. What's below is associated information that's not part of the primary key. So from earlier you already saw the mouse, to define it, you need the mouse ID. That's a primary key to uniquely identify it. And every other information are not the uniquely defining information. So that's why it goes under the dash dash dash. So I define DOB, date of birth, and sex. Equal means this is a default value. Just like the function you can define in Python, you can pass default values in case someone forgets to enter the information. So I'm basically saying date of birth can be null, meaning empty, in case you didn't want to enter it. And sex can be unknown. As far as the data type, date of birth is a date. This is one of the accepted data types, and it will represent, as you expect, a date with the year, month, and day. Now the sex is unknown, the default, but it really is a data type called enum for enumeration. It's not the enumerate for the iteration. Enumeration, in the sense you can specify a couple valid values. It's like a drop-down list. So basically I'm saying a valid value for sex is M for male, F for female, or unknown. And it defaults to unknown, which is a valid value. So all that just going into this small line of code defines the table. And by running it, you have actually successfully defined a table, and this table now actually exists on our cloud database. Yes?
So when you did date of birth equals null, that null is not a string, right? Null.
Null is not a string. Null value is like one of the specially accepted values, meaning it's empty.
Okay. So could you have put none there
But
as
it's,
well?
yeah.
You couldn't have put none, no. So this is a bit specific syntax. Yeah. So none wouldn't work. You could make it work, but none currently doesn't work. It will panic. All right, so you can actually look at the table you created by just instantiating the object. So here, you create it, it has nothing in it. Shouldn't be surprised, right? You just created a table, you didn't put any information in it. So obviously a table without any data in it's pretty boring, so let's go insert. I here show a couple ways to insert information in it. You can insert as a tuple, where a position indicates what data it is, or you can insert a dictionary, where the key is the field name and value is the value. So I'm not going to step into detail. This is where, if you are interested, you're referred to my workshop or tutorial, where I really go line by line and step through everything here. Here, this is the quick survey, so I just run these in sequence. And at the end, what I achieve is a mouse table that has a couple entries in it. Right? So you can see, at least for mouse, we're now starting to do a good job in organizing our data. There's enough information to uniquely identify mice. There's a mouse ID. And per mouse, you have associated information like date of birth and sex. Okay, so far so good? Makes sense? Now we have mouse. Let's actually check a couple of things. So one of the benefits of putting your data into data join is that it gives you ability to get data integrity. So what do I mean by that? There are a couple things, a couple aspects of data integrity, but one of this is that you don't have a way to create a duplicate entries if you're actually using data join. So for example, here, I already have a mouse with ID 0. What happens if I try to enter yet another mouse that has mouse ID 0? Well, if you try it, it basically panics and tells you data join error. And if you scroll down, it says duplicate entry 0 for the key primary. This is their way of saying you already have an entry that has a primary key ID of 0. And because this cannot be made sense of, right? Even if it's the case that you already have identical mouse and maybe the rest of the information was identical, it's far safer for us to say you already have an entry for that. So this was done as a duplication. Or maybe if you're actually trying to enter same mouse ID but with different values, there's definitely something wrong going on. It might actually be pointing out the fact that somewhere in your lab you have two mice that have same mouse ID that then becomes a bigger problem than data join. You guys have to figure that out and probably rename one of them and give a new ID so you don't have a duplicate. Or maybe in the way you're inserting, you had an error. You actually meant to type maybe 100 and just forgot the first 2 digits, or something happened and you entered 0. It will not create a duplicate entry. It would just error out saying you already have that entry, check what you try to do. So this is one of the benefits of using data join as your backend data organization system, is that it checks for integrities like that. Now, having a table that houses all your data, but without being able to access it, is also as boring. So you want to be able to get the data out of your tables. Otherwise, you're just going to be able to look at it, and you kind of be like, oh, and that's how your life is going to end. So you want to be able to interact with the data you put in, and that's where you get to fetch the data. So if you take your table and call fetch method on it, well, it just fetches everything. It fetches every data in that table. So here I have a couple of entries. It fetches in a special format called a structured array under NumPy, which is kind of like a mixture between NumPy array and dictionary. I'll let you play around with it or read around. Again, if you're curious, do go to the tutorial. I talk at length about what this means. Another way, though, is like you might not want everything about the mouse. Maybe you just want a list of all the sex values. In that case, you just pass in the particular attribute or column you're interested in, and you fetch that, and it will just give you a listing of all of that entries. Okay, so far so good. Makes sense? We'll look at far more interesting ways of getting fetched, but at the moment, at least you can fetch all the data. You can get a dump of the table. Now, this is where it gets interesting. Data join actually comes with very strong and more powerful query language, but that is trying to be, and it is very intuitive. So what do I mean by that is this is by way which you can manipulate what is it that you're trying to get out of the table, and by using query language, you can really just get to only the data you care about, so you don't have to fetch everything all the time. And you can almost think of it as a search. That's one other way to think about it. So one of the key ones is restriction. Restriction is by which you can narrow down your search. It's kind of like a filter in your shopping website. So here I say I only want mice that has sex of M, male mice. I restrict it by string that says sex equals M, and it only returns me the mice with male or M as a sex. Okay, another thing I can do is I want to only look at mice that were born after 2017, January 1st. Or you can just pass in a restriction with an inequality. Date of birth, DOB, is greater than 2017 0101, and you get the appropriate entries back. You can also combine these together to make arbitrarily complex filtering or selection and restriction. You can say, I want mice that are not male. Now, that's not the same thing as female because they're unknown. So that means female or unknown. And date of birth is after January 1st, 2017. You get the appropriate entries. In this case, there are no unknown that match this criteria, so you only get female with the appropriate birth dates. Another nice thing is that you can actually build your query step by step. So first of all, you can get and search for one thing, store the result as a variable, and then use that in your next query. So here, for example, I'm going to first find all the female mice and store it. Here I get a female mice. And then on top, I'm going to say, then among these born after January 2nd, 2017, and this is what I get. Okay, so this is only one out of many operators that exist in data join for query, but just with restriction, you already are achieving a lot. And finally, once you query the result, you actually want to get the result. So this is where you get to use fetch. And straightforwardly enough, all you have to do is get the result stored in a variable, and you can just fetch that result. So you only get the restricted values back into your working space. And you can always just do all in one step. So I put in parentheses, mouse restricted with sex equals M, and then fetch it. That restricts and then fetch it all in one step. Okay, so far so good? Make sense? Yes.
So when you just query and you get a table, that's different than fetching it.
Yes, that's a very good point. So when you're looking at the table that's shown, that still is just a preview of what's on the database. Until you say fetch, it doesn't actually get all the data. Now you might be wondering, well, if it's showing this, isn't that just already transferring the data? To some extent, yes. But as we'll see, once you actually start having much more complicated data, where part of the data information is like, say, bunch of spike times, it wouldn't actually show you because it actually wouldn't get that information just for preview sake. You only preview stuff that is easy to just grab. And also, if you have a lot of entries, it will only show you the first 10 entries or so. So you can get a sense of what's in the table, but without having to take all the time to download all the data from the database. Only when you say fetch, then what's currently part of your set of entries in the table finally gets transferred over. So you have a lot of opportunities to narrow down with your query language, narrow down to exactly the entries for which you want to get the data from, or data from the database, so that way we don't waste a lot of the network connection or even local memory just holding all the information. All right, so now we actually kind of explore how to work with mouse. We're kind of going a bit too much on one table, so let's actually make it a bit more interesting by extending to the next table. So next along the list of the things that we want to represent was an experimental session. So just like we started with the mouse, like what is it that uniquely identifies a mouse? We asked the question, what is going to uniquely identify an experimental session? So if you kind of read the information further, I kind of gave you a bunch of hints saying like, you never work with more than one mouse. You work with more than one mouse in a day. But for one mouse, you don't work on more than 2 sessions within a day. So that means combined together, a session can be uniquely identified by knowing which mouse is it that you're working on and which date the session was performed. It's a combination that's unique, and it's not either of them alone that could uniquely identify a session. If you just tell me mouse ID, there could be many, many sessions that's done on that mouse. You hope that's the case. But if you also tell me just the date, I could have done more than one sessions across different mice. So in order to be able to narrow down to one experimental session, you need both information, the mouse ID and the session. Or a better way to think is the mouse you need to represent, and on top of it, the session. So given the fact that session is always about a mouse, there's a dependency. Or we call this a dependent relationship, or if you were to go in the lingo, we have a foreign key restriction, a foreign key constraint. But just think in terms of dependency. Every session depends on a mouse. A session cannot exist without a corresponding mouse. So you can visualize this kind of relationship by plotting something called an entity relationship diagram. It's basically a fancy way to say how objects are connected to each other, or how things are connected to each other. If you were to plot it, the relationship looks more like this.
Sorry for
Sure, go ahead.
hanging on this, but so when you say a foreign key constraint, you mean like for the session the mouse is a foreign key constraint, or why?
Yeah, for session, mouse is a foreign key constraint, exactly. So session cannot exist without a corresponding mouse entry. Yeah. So given a session, you actually depend on mouse. That's what's depicted here. And when you define the table for session, you actually reflect this fact. So if you look at this, so here and now we're defining a session table. Now you actually see that we actually have the special syntax with an arrow pointing to mouse. This suggests that a session depends on a mouse. Okay, so anything that is needed to uniquely identify a mouse will be automatically part of a session. But on top of it, mouse is not enough to identify a session, so you need an extra attribute that's going to be the session date, the date on which the session was performed. So these things together is now the primary key for your session. Together, they uniquely identify a single session. And on top of that information, there are associated information per session. We want to keep track of the experimental setup, for example. So that would be, say, one integer that just is a numbering of the different setups. Or you also might want to keep track of the experimenter that performed the experiment. So that could be a string. In data join lingo, you specify this as a var_char, means variable length character. It's just a way to say this is going to be a couple character long string, and you get to tell up to how many characters are allowed. So here var_char 100 means you can use string that is up to 100 characters to describe it in case your experimenter has a very, very long name. Okay, so you can go ahead, run this. Again, that defines that table. And you can actually get the plotting, this ERD thing that shows you relationship between the entities by calling dj.erd function onto the schema. So that, remember, schema is the collection of all these tables. I've been putting all my tables into schema. So if I plot the schema, it gives you ERD for all the tables that are part of the schema. So here I successfully gotten the same figure. So I get the mouse on top and session on bottom. This is their way of saying session depends on mouse. Okay? All right, so now to get a bit more concrete for you, let's actually start inserting data into it. So first of all, here's the data. So now I'm using dictionary. Yes?
I think the ERD is not working for
Yeah, it's not working for me either.
Yeah, what does it do?
Invocation exception.
it's a
Graph is executables not found.
So graph is missing. Yeah, so this is probably where if you would have used the conda, it would have worked. Okay. I will make note of this. It totally fell out of my mind, the fact that graph has to occur. Yeah, so this is exactly, I guess I could say, this is exactly what happens if you use pip, is that things like GraphViz, which is an external library, needs to be present on your machine for data join to work. But that's actually also because it's just using slightly older version. But yeah, sorry, I'll make note of that and try to fix. So that for you guys, skip the ERD because that wouldn't work until you put the GraphViz. After the session, I could easily tell you how to install GraphViz. It's not that hard, but it's not like a single line I can tell you and we'll fix. It will be actually a couple of lines, like 4 lines that you have to enter in. So pip doesn't understand GraphViz because GraphViz is not a Python package. GraphViz is actually a C, C++ library that you need other tools to be able to install it. This is where something like Conda could have helped. So Conda actually can deal with non-Python packages as well. So if you would have used Conda install data join, and that straight up wouldn't work. There are actually a couple other additional things you have to put in to make it install data join. And aside from the fact that that version of data join is a bit outdated, you would have also installed along with it PyGraphViz on Mac. We haven't configured the Conda perfectly to the point it would have worked on Windows. So for you guys, in ONO, it would have needed extra step to get this up and running. All right, so my apologies. I'll make note of that. In the future, I would make a different way of actually getting this running. So, I mean, at least it's not that big of a graph, so you can just appreciate what it would. If it would have worked, this is the beautiful graph you get out of it. So just appreciate that fact, and just have hopes that one day you can actually plot ERD should you decide to do so. So here, what I'm doing, I'm just entering a bunch of information, additional sessions. So I'm using the dictionary notation since it's easy to specify each entry. So I'm entering sessions for each animal. And you have to specify all the fields, at least the one that doesn't have a default value. So obviously, I always have to specify the mouse ID and the session date. And that's why I'm taking care not to make a duplicates or anything like that. So after 3 sessions entry, this is what my session table now looks like. So it has 3 sessions done. And this is also now we get to do a bit of integrity check. What if I try to make an entry of session for a mouse that doesn't exist? So here I'm trying to make an entry of session for mouse ID 9999 that doesn't exist. If you try to run it, it actually gives you a, sorry, I didn't actually run it yet. If I run the insert, it actually gives you a very lengthy error. I just started saying integrity error. And yeah, I have to admit this is a bit cryptic, but basically this is their way of saying like you're trying to add something for which there's no corresponding parent entry. It's the same like, hey, you're trying to make an entry for which there's no corresponding mouse. Like that kind of mouse doesn't exist. So this is another benefit of using data joint. It's not so much the scary error portion, but at least check for you is that every time you're trying to make an entry of the data, and if it depends on other tables, it will make sure that you have corresponding entries in what you're supposed to depend on. Since a session depends on a mouse, if you're trying to make an entry in session for a non-existent mouse, you cannot make it. Data join would ensure that that wouldn't occur. Okay, so this is 2 things so far. Integrity, you cannot make a duplicate entry, and you cannot make an entry for a dependency that doesn't exist. All right, so now we have 2 tables. So we have a couple entries in the mouse and then 3 entries in session. We can even do a bit fancier query. So first of all, you can actually restrict one table by another. So if I say mouse restricted by session, this translates to saying all the mouse that has a session. So since we only had 3 sessions, at most you can get 3 mice. In fact, you only get, I think, 2 mice because one of the sessions was for the same mice. 2 of the sessions were for the same mouse. So you get 2 mice. So this is a quick way to say which mice have been recorded under some session. This one is a bit fancier. So basically, you can think in terms of steps. First of all, you should already know the mouse restricted by sex equals M means male mice. And now I'm saying, give me all the sessions on male mice. That's what this restriction means. So here, if I run it, I just get the entries of session that was done on male mice. So in this case, mouse ID 0 was the only male, so you get the 2 sessions for that mouse. But the other one, I think, was on mouse ID 100. That's not male, so you don't get that back. If you want to see all the possible combination or valid combination of mouse and session, you can use this another operator called join operator, which is a multiplication sign, to kind of have a mesh of all the information for valid entries. So it finds all the mouse for which there's a corresponding session, and then put the information together. So you find information not just mouse ID, but you also find the date of birth and sex for that particular session entry. So this is, if you were to look at all of them together, combined, you can actually do join to get information at once. All right, so hopefully that made sense. right? Now again, if this feels fast, it is supposed to be fast. I don't really expect you to be a master of data join after this session. I'm really trying to give you a bit of an idea of what using data join could feel like. Now, one other interesting and important thing is once you start performing experiments and importing data, working with data, ultimately speaking, there's some data recorded that probably happens in forms of files, for example. So in our scenario, we already talked about the fact that our recording system actually produces a data file for raw trace for every session you perform. So what you might want to do is to get the information from file and put it into your table, or put it in a table so it's now part of your data pipeline, so all the information could be found in one place. So here, basically what I've done is I provided in the data directory. I'm not going to really look in it. If you look at the data directory, there are a couple files that looks like data underscore blah, 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 blah. And they actually just have a very strict convention in that it's the first portion. So for example, it has a convention of data underscore something underscore what looks like a date. And that's exactly what it is. It's data underscore the mouse ID underscore the session date. That's the convention for the files that's, say, produced by our recording system. What that gives us is that for each recording session performed, there is a way for you to tell which file is the recording that corresponds to the session. Okay? So now we're going to look at is how can we actually get this information. So these are individual neuron recording from that session. And now we're going to try to represent that information in our table. And since this is about neurons, we're probably going to call this table neuron. It's another thing in our whole experiment. So before we do that, let's actually just practice loading the file, because if you don't know how to load the file and deal with it, you really cannot deal with this. So we've already seen in the past how to load the NumPy data format. So this is actually given as a NumPy file. So if you just do np load the file, you should be able to load it. This is the part where if you run it, obviously it's going to just fill your screen. Kind of fills the screen. I'm just going to collapse this. Let me go up and collapse it. Okay. It would have been better just to see the shape first. So hopefully this is a lesson you're learning, is like before you actually just look at the data, you probably want to take a look at the shape so you wouldn't be shocked if your screen just gets filled with the data. So here was 1,000 entries. So 1,000 is this borderline length where the NumPy quite decide not to truncate it for you, just shows you the whole thing. If you had something like 10,000 entries, it would have truncated and not tried to show you the whole 10,000 entries. So 1,000 was a bit too short for that, so it showed the entire thing. I guess that's acceptable. And in the other session, as I said, you always want to make sure you try to visualize your data to get a sense of what is going on. So here, if I just look at it, it looks like a fairly noisy spiking raw traces. Okay? Okay, now we get to define table that's going to house this information. Ideally, what I want to do is for each neuron recording, have a corresponding entry in the neuron table. So again, the same question occurs. How can I uniquely identify a neuron? What does it take to uniquely identify a neuron from my whole experiment? But if you went back to the information, I actually would have said that per session, I only do a single neuron recording. Meaning that if you actually know the session, that is enough to identify the neuron. There's no more information needed to identify one neuron. So in this case, the definition in the neuron is going to be straight up dependency on session. So neuron could be uniquely identified by the session in which it was recorded. So you'll have a straight up dependency on session. And you don't need any other attributes or any other columns to further uniquely identify it. So in the table definition, you would have used definition and just point to session, and that's all there is to the primary key. Now, associated information in this case would be the loaded neuron spikes or neuron raw trace. So I want to have the actual whole NumPy array be stored in my table. So that's not going to be quite an integer. That's not going to be quite a float. It's not even a varchar. You're going to use the special data type called long blob. It just stands and basically gives you ability to store fairly arbitrarily data types and just store inside the table. So a long blob actually can store up to 4 gigabytes per entry. If you actually want to go over that, there are other data types you can configure. But at least for long blob, you can go up to 4 gigabytes per entry. And with 1,000 entries, that's not anywhere close to 4 gigabytes, so we can safely store that information as a long blob field. And I'm going to call that activity. That's going to be a column called activity per neuron. So hopefully that makes sense. and I just defined it. And again, let's just take a look at the ERD. This is not going to work on your guys' machine, so just appreciate it up here. So it extended it, but notice now it's in different color. Neuron is color blue, unlike the green rectangles we've been seeing so far. And the reasoning is that, I don't know if you noticed, but if you look at the class definition, I'm actually not inheriting from DJ manual. I'm inheriting from this other class called DJ imported. So this is where you get to talk a bit about data join tiers or table tiers. So this is just a way for data join to indicate for each of the thing or a table, what kind of information can you expect? So far we've been only doing manual because these are information you expect a person or maybe a recording system to manually enter information from outside. Now the neuron is a bit special because information came from an external file. So as you try to insert information to neuron, you will depend on the data file. And whenever you have this external file or external source dependency, we recommend you use something called DJ imported to indicate the dependence. On top of it, it's going to give you a nice mechanism to actually automatically perform the import. And that's what we're going to quite quickly take a look at. So imported table and data join ERD is represented by this bluish circle, bluish oval. Okay? So what we get to do now is automatically try to import. So what do I mean by automatic? Well, the thing is, we know that each neuron is uniquely identified by a session. And in fact, if you know a session, that's the same thing as knowing the mouse ID and session date. And we know that each data file is unique. If you know, you can identify the data file by knowing exactly those information because it follows a very strict naming convention. So that means that because I know all the sessions, and because I know the file conventions, I can just go through all the sessions and one by one visit the data file and import the data into the table. So I can kind of automate this process, just define how to do it right once, and just let the data join handle the process of going through all the sessions and performing the import. And to do that, we're going to take care of data join's make and populate mechanism. So what you do is you define a method called make inside the table. So I'm actually just revisiting the class definition, but here I'm adding a new method called make. And make is a special method that's going to get called with one key. And that one key is an entry from a table that it depends on. So here, because neuron depends on a session, the make is going to get called for every entry of session, but one at a time. So with that understanding, what you have to do is that given that particular entry of session, you have to define how can you open up the corresponding file, get the data in, and create the necessary table entries, the columns that you want to store. So here what I do is, given the key, which is going to be a corresponding actual primary key information, that's how it's going to work. So primary key of a session, that's what this parent is. So primary key of the session would be the mouse ID and session date, and it will be coming as a dictionary. So I'm actually using a bit of a trick. Basically, this is the same thing as saying, like, fill mouse ID key value in there and fill the session date key in there. This is a bit of the key expansion trick that I haven't taught, but this is how you can learn new tricks. At the end of the day, basically it just correctly comes up with the name of the file. It opens up the file, which we know is going to be just a NumPy array. And then it stores that information, the activity, as part of this entry. So key is a dictionary you're building up. It already came with two entries for mouse ID and session date. So now you just add new entry for activity, fill it with the data you just loaded from the file, and you insert it into your self. Because self here is the neuron table. So I know it's a bit of convoluted mechanism. You should try to go a couple of times. Again, I'm not going to really spend too much time talking about it, but this is a way by which you get to define how is it that knowing the dependency for neuron, which is that each neuron, one neuron per session, you can visit every session and identify how to get the file, open it, and get the necessary data out of it. You can actually populate the neuron table. So it's probably just better to see it in action. Now you kind of have a rough idea how it works. You're going to actually get to trigger the make call on every session table by calling populate method. This is the populate make logic for data join. And if you call populate, what it did is actually call this make method 3 times, once for each of the sessions. So we had 3 sessions, So you call make once for each of the session, each time giving enough information to identify the session you're working on right now. So here it's basically printing a message because that's what I added at the end to report what was it they worked on. And most critically, you look at the session, there are 3 entries, and now there are 3 corresponding entries in the neuron. So you can see there should be one-to-one correspondence because for every session there should be 1 neuron that exists. And there's this extra attribute called activity, which is actually the whole NumPy array you loaded. Notice it doesn't show it because it will be a very lengthy information. And this is just a preview. This is where you're actually not really fetching all the data. This data actually exists somewhere in the database, and it's just giving you a preview. If you want to see the data, you get to fetch it. So if I had to take a neuron and fetch it, you get all the activity traces for the 3 neurons you just have repopulated. Okay. So if not everything made sense, that's fine. Hopefully you get the idea of the logic where by establishing the dependency, DataJoin can tell which tables or which entries from the session the neuron have to work on and try to populate itself. So get the necessary information to make a corresponding entry inside the neuron table. And this is the whole mechanism behind imported table. So you can define how to do it right once, and then you can continuously do it for future. Okay, sort of makes sense? All right, and so finally the last chunk of topic is how to define computation in data pipeline. So just like you're now representing things that in your recording, so started with real objects or real things in the real world like mouse, and then we move on to things as a conceptual grouping such as sessions, and then even went on to again, some realistic thing like neuron. So we have representation in building up our pipeline. Now we actually get to do some interesting computations on it. The key here is that when you compute stuff, ultimately you're trying to compute something, another thing. So you get to just take the result of your computation and represent them in a table. Another table for things, and you just call it by the name of whatever you computed. So this is the way by which DataJoin pipeline can not only represent the original data source and even imported data from files, but also computation results. So it really can capture everything you do in an experiment in this whole pipeline as a workflow. So here what say we want to do is like now we know that there are activity traces or a whole raw trace represented in neurons. For each and every one of those neuron activity, I would like to compute some basic statistics. Maybe something like mean and standard deviation and the maximum value. So you can do that again by defining a table that's going to represent the result. So here I'm going to call it collectively activity statistics. That's going to be the table. Each entry of activity statistic would be set of statistic values for each neuron. And because I want to establish this dependency on the neuron data, it should be fairly intuitive that I'm going to have dependency from activity statistics back to neuron. This basically says for each neuron, I'll have an entry in activity statistic, which should represent the statistics you compute on the activity information. So we can go ahead and define that table. I'm going to call that again activity statistics. It's going to have a dependency on neuron, and that's it. Right? This is one-to-one. For every neuron, there will be a corresponding entry in activity statistics table. And associated information that gets stored, that's the real thing that gets computed and stored, would be a couple of statistics such as mean, standard deviation, and maximum. Okay, so that's how my definition goes, yeah?
Can you have one-to-many dependency?
You could have one-to-many dependency. If you're going to have one-to-many dependency, though, you have to still be able to uniquely identify each of the entries on the many side of the things. So if you had, say, other ways by identify one entry of activity statistic, you just have to add the necessary thing it would take to identify it. So if it's one-to-many, that means per neuron, you're going to have multiple entries of activity statistic. So there have to be some additional information, like additional attribute that will be part of the primary key. Right? Yeah, so that makes sense. All right, so you can run this. That will at least define that table again. And again, you can plot the DJERD to see how far we built the pipeline. And this time, you notice that it has added yet another table offshoot of neuron, but has yet another different appearance. And that's because, again, we changed what we inherit from. We no longer inherit from manual. We're no longer even inheriting from imported. We're inheriting from dj.computed. Again, the tier, these are called tiers of the table, represents the kind of the data you'll find. So manual, again, was something that comes from outside, entered either by experimenter or recording system manually, so to speak. And imported, shown in blue ellipses, are data that's imported from some external data files. And that allows you to also take advantage of this make and populate logic. Computed tables shown in red circles are data that you compute, but by using data that's available in other tables, but not using anything external to the tables. So meaning that you compute activity statistics using information only available from within the data pipeline without trying to fetch and get data from some other files. Right? This is important because when it comes time to backing up the whole database, you have to really know who's super critical. If you have a dependency on external data, that means if you lost that information, it becomes much harder to recover. Whereas if it's computed based on what's just purely available within the whole pipeline, you could potentially lose that table, but you can just recompute. Every information should be available entirely within the pipeline. So this means that if you were to have a priority on who should be backed up, imported should be much more important to be backed up than the computed tables. Manual tables, since it's manually entered, also tends to be pretty difficult information to recover. You do want to back them up fairly frequently as well. So this is more of like indication of where the dependency still occurs. Again, like since Neuron already imported all the activities, technically you could get rid of all the data files, the raw data files. Information is there, but that is a risk. You would not be able to recreate this from scratch if you lost the raw data traces. So every time you encounter a blue ellipsis, it should just be a note in your mind that it depends on some external file. And if you need to really recreate it, you need to know where those external files are. I mean, if you just have it backed up, technically you have everything you need. So you may not need to worry about it. It's just something to be aware of. Okay? Also, red computed doesn't mean you can go ahead and delete it all the time. Some computation takes forever. Like if it took, say, a week to compute it, you don't necessarily want to delete it and recompute. That's another week you're just spending on it. So how expensive it is could still depend on exactly what table you're talking about, but how irreversible the effect of deleting something fairly could be well indicated by the tier of the table. That's what the tier of the table are really for, or at least one of the purposes of it. Okay, so computed table, aside from the fact it doesn't depend on an external data source, is really a lot like imported in that it can actually have a make populate logic. So here idea is that activity statistics should be computed for every neuron. So if I define how to compute all the statistics and make an entry based on the computed statistics once, DataJoin can automatically visit every single neuron and make corresponding entry in activity statistics one at a time. That's the whole make populate logic is about.
So
Go ahead.
the make, it will automatically take the category in which it's dependent and make it the self, and then take what you're putting in to be the key.
Yeah, so basically the way it works is that since here activity statistic depends on neuron, it goes through and visit every one neuron at a time, put the necessary information about the neuron in the key, okay? And self still points to the table you're populating. So self is the activity statistics. So that's why when you say self-insert, you're inserting a new data into this table, which in this case would be activity statistics. So hopefully I clarified it. All right, cool. So let's define how to compute statistics, right? So here again, I'm using a bit of tricks that's really not detailed because I skipped over when I'm trying to create this in condensed version of this. But hopefully you can get an idea. Basically what I do is as I visit the key, so key is what can uniquely identify one neuron at a time because that's what I depend on from activity statistic. I take a neuron restricted by a key. Key can narrow it down to exactly one neuron because that's what the make logic would do. You depend on a neuron, so visit one neuron at a time. The key corresponds to one neuron. So if I restrict the neuron table by key, it gives you exactly one neuron entry. I'm fetching the activity for that neuron. Again, that's a long blob. It's a NumPy array. So when you get it back, it's a NumPy array. That's my activity. And given it's a NumPy array, the rest is pretty straightforward. I just compute the mean, standard deviation, and maximum, and now store them as an extra attributes or columns for my own table. So I need the mean, standard deviation, and maximum fields. So I just put those information in as additional entries in my dictionary. And finally, I insert the completed dictionary onto myself, making that entry. And just for bonus, I print out a message saying I just populated this. So because if you don't do this, there's no messages printed out. You just silently do all the jobs. So putting this in can actually help your mental sanity. So here I define it. I'm still not populating it. Now if I populate it, it goes through every one of the neuron. And you can look at the result. It has successfully computed mean, standard deviation, and maximum for every one of those neurons' activity. So hopefully you see this is a mechanism by which you can just really start to follow this pattern. Define it once correctly, and it will apply it everywhere. Okay, so this last section I was going to go if I felt like I had enough time. I think I have enough time, so I'm just going to quickly go through. And this is yet another computed table, but it does have one more twist in that it has a parameter that controls the behavior. So this is actually a spike detection. This was actually part of one of the notebooks I provided as a bonus. It actually does use the exact same logic. So if you've already seen it there, you know what this is going to be like. If you haven't seen it there, this is your chance to look at what spike detection, a rudimentary spike detection algorithm could look like. So here I'm using a special syntax to fetch key, and key all capital letters, that gives you only the primary key attributes. And if I just use a key now to restrict back the neuron, because I fetched every primary key attribute, this really doesn't restrict anything. It gives me all the neurons. So if that didn't make much sense, don't worry too much about it. All I'm doing is like just getting all the activities. And here I'm just plotting all the activities as subplots. So here you can see my favorite subplots logic of figures and axis. I'm zipping them together, so I visit them one at a time to plot them. So I basically get 1x3 plots for all the 3 neuron activities. Okay, so they all look like some sort of spike activity traces. Now I basically decide on one key, so one neuron activity, or one neuron. And for that neuron, I get the activity. So there should be now only one activity trace. And I plot it. So basically I just chose the first one. And here I changed the x limit, meaning I changed the x-axis so that I'm only looking at a very small portion of it. So you have a bit more zoomed in version of this. So now let's actually just quickly think of how to do a spike detection. Spike detection is often about when something crosses a threshold. So if it goes above a threshold value because it just did an action potential spike, that's when you say, okay, this is when it had an action potential. So you can threshold and find everywhere it crossed, or everywhere it's above the threshold. So this is orange line showing wherever it's above. So 1 means it's above, and 0 means it's not above the threshold. So you can binarize this like this. And we're not quite interested in knowing where it was above. We're only interested in when it went above. And as long as it stays above, we're not that interested. We only care about when it went above, because that's when one action potential occurred. At least that's the definition by which we're going. So here I'm just doing a bunch of tricks. You can actually get a detailed view of this from the other notebooks, or if you read this a bit more carefully, it basically shows that I find where it crossed and I mark it with the red dot. And I basically take the times that this red dot occurs, so this rising edge of the threshold, to be where a spike occurred. So that's my interpretation of spike times. So this is a very rudimentally, but at least well-behaved and well-defined spike detection algorithm. And so this all gets stored in this variable called spikes. It's a NumPy arrays of zeros and ones when one occurs at the spike time. Oops. And I can actually just add them up. Since one occurs every time there's a spike, if I add them up across, that gives me total spike counts. So in this particular trace, I had total of 26. You don't see whole 26 because I'm only giving you a narrow window view. The whole algorithm actually applied over the entire trace. So here was total of 26 spikes. Now this is the part you can actually play around with this. The threshold does matter. So here I'm basically put all of those into one cell so you can just play around. If you change your threshold, your total result changes, right? So here, if I just run it again with 0.5, Again, this total spike count is 26, same exact thing I just ran earlier. But now if I change my threshold to something smaller, so say maybe I'm going to put my threshold to 0.2. So as soon as it goes above 0.2, I'm counting that as a spike. Well, I get far more number of spikes. Now, according to this, there are 57 spikes. And if you compare against data, you probably will be pretty doubtful whether that's a good assessment. If you want to be really conservative, maybe I'm going to say threshold should be 1.5. Only when it crosses 1.5, I'm calling that a spike. Now I only get 13 spikes. So half as much if I use 0.5. So you can, and it seems to be missing some area you probably would identify as spikes. Like these look like pretty well identified spikes, but with the threshold of 1.5, I'm totally missing them. So the message here is that even with this simple algorithm, you can have a strong dependency on what we will call parameters of your algorithm. In this case, a parameter is a threshold. By changing the value of the threshold, you will get different results. And if you're going to ask me, like, okay, what's the right value of the threshold? The short answer is usually I don't know. There's usually not a perfect answer to this. Oftentimes, this is going to be empirical, meaning that you basically get to try different values. You have your own ways of detecting and assessing whether it is actually doing a good job or not. You can be as quantitative as you want and come up with a bunch of theories about. You can employ something like Bayesian statistic methods that says like what's the likelihood that this is a correct assessment and such, or you can just go with your gut feeling and say 0.5 feels right, 0.5 it is. You might be thinking I'm joking, but it's not. Surprisingly, this is actually how a lot of things are getting done. So the problem is not so much that there's dependency on what might feel like an arbitrarily parameter choice. The problem often is that this very choice of parameter is not conveyed. So when someone runs a detection algorithm, like just in this case, I could have easily just described this algorithm in a couple lines of code, just as I'm doing here. But if I don't really tell you the threshold, you don't know the whole picture of what was happening with my algorithm. The parameter choice is critical. And in literature, things like this are often lost. It's these subtle points. It could even be treated as a minute points, but when it comes to trying to reproduce a result, you can imagine like difference between 13 to 26 to 54 spikes matters. Your data would be, your assessment could dramatically change according to what was the threshold you use. So hopefully, of course, there's some logic that goes into what's a reasonable threshold. It's not an arbitrary choice, because if it was completely arbitrary, you would probably just tweak this until you get the result you're looking for. In terms of downstream analysis, right? You might actually just do it until you get the positive result with p-value less than 0.05. Obviously, that's not how it's supposed to be. You should have a bit more logic and reasoning behind it. But nevertheless, at the end of the day, you have to make the judgment call, or someone made the judgment call as to what is the threshold that gets used, and that ought to be documented somewhere. So now what we get to see is actually building these things in the pipeline itself, so you don't have to have a separate notebooks hidden behind like a bunch of tables and a bunch of desks that you finally get to really figure out what the parameter was, or maybe deep dive into like 10,000 lines of code to finally find the one number that actually controls it all. Rather than making it like that, you can actually be very explicit and actually store it as a table of parameters, with the added benefit that you can actually try different values side by side to compare results and dependency on what happens if you would have used different thresholds. So this is where we get to define, first of all, a new kind of table called a lookup table, which is just going to store our parameter values. So here I'm actually doing this thing where each lookup table is going to be, an entry of lookup table will be a parameter. In this case, there's only thresholds, so you might feel like threshold values should be uniquely identifiable. The only problem is like floating point is hard to say if it's identical or not. Like even if it looks identical superficially, say between 0.066 and another one that looks like 0.066, if they're off by 0.00000001, they're two different values. So to avoid that potential numerical precision error confusion when it comes to comparing floating point numbers, it's best not to use float point numbers as your primary key, but use something else as a surrogate. So in this case, we're just using ID that I'm coming up with. It's just going to increment as I add new values of threshold. Here I'm just going to call it SDP for spike detection parameter ID. And the associated value is the actual threshold, which would be a floating point number. So here I'm defining it as a lookup table because this is just a place where I'm going to store a couple of values. It's not a manual table because it's not really about your day-to-day experimental recording. This is something that once you define it well, it probably wouldn't change much. Maybe I'm going to have up to like 5 or 6 values of threshold values that I'm going to try, but it really wouldn't change much. I'm not going to keep on accumulating. So those kind of information where it's relatively going to stay fixed is best represented by a lookup table. Practically speaking, this also means they don't change much. They don't have to be backed up as often. So here I just created a lookup table, added to the schema. Since it's not connected to anything, it's just floating by itself. We're not using this table yet. So let's go ahead and define our spikes table. So unlike previously where neuron only depended on session and activity statistics only depended on neuron, we're going to have a table that represents the detected spikes or spike times. That's going to depend obviously on neuron because it's going to be about spikes from a neuron, but also on spike detection parameter because it's to do these together combined that determines what is the final set of spikes you determine. So you're going to have dependency on both the neuron and spike detection parameter. It's the combination of those two that uniquely identifies a particular spike set. So each combination is going to have spikes in a long blob. It will be spike times, so it will be zeros and ones where one occurs at when the spike was detected. And just to make it later on easier for yourself, you're going to also go ahead and compute the total number of spikes and put this as another attribute so it's easy to later just get to it. Obviously, you can always fetch it and take the sum, but you don't want to always go through the fetch and summation process just to get spike counts. So for commonly looked up information or information that you're always interested in, you might as well make an attribute or column and have it computed once and store it. So this is how we're going to define it. And if you now look at the ERD, this is what it looks like. So now you see that spike detection parameter is brought lower down because it's tied down to spikes. Spike depends on neuron and spike detection parameter. It's every combination of those two that uniquely identifies an entry for spike or spikes. Okay, so the only thing left to do is, given this a computed table, is to define how for every unique combination of neuron spike detection parameter, how to compute the spike train and put it in yourself. So logic itself is identical to the algorithm I was demonstrating earlier. Only difference is that you need to get the activity yourself based on the information about the neuron you depend on. And also the threshold is now something you get from the spike detection parameter table. So that's what the first two lines are in the make, aside from the print. So you say neuron, get that particular neuron, get the activity. And similarly, for get the spike detection parameter that corresponds to your key, and just get the threshold value. Given these two values, the rest of the computation are identical as my spike detection algorithm earlier. I just get to the spikes. I also go ahead, count the total number of spikes, and then finally I store them into the key and insert into myself, completing the computation of the spike train and total spike counts for every combination of spike detection parameter and neuron. Make sense? Okay, so with that all defined, let's go ahead and look at the spikes table now. Should be empty. We haven't populated it yet. And we get to populate it. So you co-populate, nothing happens, right? So nothing happens because spike detection parameter is currently empty. So if you're only going to do valid combination, there was nothing in spike detection parameter, so there didn't exist any valid combination to compute for. So in order for this to work, you have to have at least one entry in spike detection parameter. So what I do is I came up with one entry. I'm going to use threshold of 0.5. Remember, it needs the spike ID, something that you've just put in. So I'm giving an ID of 0. So I'm inserting 0, 0.5. And after that, my spike detection parameter does have a single entry. And finally, if you go to spikes and run populate, it will now run for every neuron and spike detection parameter combination. So that should be 3 entries to be computed. It runs the spike detection algorithm. And finally, you can see in the spikes table the detected spikes in blob and associated counts. Okay? So hopefully you can start to see the power of this. If you define it well once, you can even compute for every valid combination of parameters and data. And you can even see the power further by having yet another threshold value. So just go ahead and insert one more threshold value to try. Give it a different ID is 1. Value is threshold of 0.9. So now spike detection parameter has 2 entries in it. Now if you do populate on spikes, it does it for every valid combination. It will skip over once it already computed. So it hasn't computed all the 3 neurons under threshold of 0.9, so we'll go ahead and compute that. And now you have results of threshold of 0.5 case and threshold of 0.9 case side by side. So this way you don't have to change the value somewhere in your code and see what happens and then try to keep in your memory what it looked like or jot it down roughly to see what's the effect of the threshold. You just have to put it in and let it be computed, and it can exist side by side. You don't have to even like delete or anything. You can keep it along to appreciate what happens if the threshold changes. So that's actually all I have for data join pipeline. I know that was already still quite a breeze, quick one through the whole pipeline definition. But at least hopefully you appreciate that now we've defined quite a number of tables, and it is already starting to be fairly functional. We actually successfully put information about the mouse, all the recording sessions you performed, neurons you recorded, the data activity imported from the files, and computed something like activity statistics, and even more complicated computation like spike detection with threshold as something you can control and change. And every one of these things exists in your data pipeline. So if you go with this data existing in the database as a data pipeline, along with the code you use to define them and put it as a package and share, that's a complete picture. You share both the data and the code that defines the pipeline. And this is the model by which we propose that you can actually achieve reproducibility from the data sharing and code sharing perspective. All right, so that's all I have for data join. I know it's already a lot to say all that I have. But just to do a very quick recap, let's get back to, I guess it just wants to know what gets into this issue. Okay. All right, so we already did this. Just a recap, so we already saw that data pipeline is, it captures the relationship between things. If you were to go with the data join terminology, it's more like dependencies between entities. Still the same thing as same relationship between things in your experiment. And you no longer have to really spread all over the place. You don't have to separate your data and pre-processing from analysis and figure generation. They can all coexist with the clear dependency between as one data pipeline. So if you want to learn more about data join, then you can visit the datajoin.io. It has information as well as how to download the packages for both Python and MATLAB. There are dedicated documentation and tutorials for this. Tutorials written by me, so you probably will hear my voice as you read through it. At least that's what people tell me when they read through it. They can hear me talking. I don't know if that's a good thing or not. There is a data join Slack group. If you go to datajoin.io, you can sign up for a Slack group, and that's where we provide fairly quick response and support for questions. There's almost always someone present 24 hours. Yeah, we have a fairly weird sleeping schedule. If it's between like 12 and 4 or 5, most likely it's me responding. And if it's data, there's also this data join workshop that was recently done with the support of NeuroNext grant that I gave for 2 days. So you can find all the information in there, and if you go to the GitHub repository with links to actual videos and all the course material. All right, so that's enough for data join. I do want to actually wrap up the session with a couple pointers as to what's beyond the workshop, right? So what's next? Well, do we want to actually take the time for you guys to appreciate how much you've learned, right? We actually covered quite a bit in this 4 weeks of 2 sessions per week course. So, we covered the Python language basics. If you never really used Python, then we actually started from the ground up. We talked about the data types, the variables. We talked about lists and dictionaries, talk about how to do Boolean expressions, and we talk about control flows, like if-else for conditional control flows and for loops for looping control flows. And we even talk about list comprehension a bit briefly by examples, and gave you actually a fairly good overview of object-oriented programming. You now know what a class is, how to instantiate a class. We even talk about inheritances in the context of both modules for the PyTorch and in terms of the data join classes. And we'll of course talk about modules and packages. We even actually created our own module, which was nothing but a script and with .py that you can import. And we talk about packages for sure, as we imported a lot of existing packages. A lot of them came with your Anaconda distribution, such as NumPy and Matplotlib. And today even installing something like data join package. We talk about the environmental setup. We started out with the workshop specific Jupyter Lab, hosted on Jupyter Hub on my own web server. But then overall, we actually learn how to install your own setup with Anaconda installation and distribution. You should now have a working code text editor. So if you ever want to code and just need something that gives you syntax highlighting, you should have something that can help you with that. You know also how to work with Jupyter Lab. If you've been following through and doing any of the exercises and any of the homework assignments, you're now pretty familiar on how to open up a Jupyter Lab and run through cells. At least the interface should be fairly familiar to you. We talk about code management. This was actually one big thing I wanted to make sure I cover is how do you go about managing and organizing your code? How do you keep track of changes? Because if you code, things like this will matter. You will want to try stuff out and without a fear of breaking it. This is where we learn Git for code tracking and GitHub as your backup system, if anything, but also as a mean of sharing code, getting code from someone else, and maybe even potentially contributing to each other's work. In the second week and beyond, we actually learned the scientific Python ecosystem. This was a big chunk. We looked at the NumPy array, which is the bread and butter of the scientific computation in Python. It represents a numerical array from 1D, 2D to beyond, which allows you to do a lot of sophisticated computations with this simple concept of arrays of numbers. Matplotlib is your friend when it comes to plotting and visualizing your data. We looked at how visualization can help you really actually get a handle onto your data, and something I completely recommend as we talk about the neural data processing. We looked at loading textual data. We saw the pains of working with the data files and having to deal with the parsing of the lines by lines and comma separated and semicolon separated values. That's something you wish you don't have to deal with. But at least you have now seen it. And with the better knowledge of some tools, you could probably skip all those pain and at least appreciate whoever did the hard work for you and just continue to use that. We looked at saving and loading NumPy data files, something that's fairly common. That if you work with NumPy, which you probably work if you're going to work with Python and scientific package, now you can save a lot of hassle just by passing around NumPy data files with each other, just giving the NumPy data. We looked at briefly on how to do processing and analyzing of the neuronal data. You load it from NumPy arrays. We look at how to do statistics, how to compute stuff, and always visualize them as you load it, right? Looking at your data is very critical. If you just look at a couple of sample points by looking at indexes, you're not going to quite get a picture of what your data looks like, and you might not be able to pick out otherwise very obvious anomalies with it. And then we also talk about basic image processing. It says image processing, basic image processing. And even more topics are there, right? But there are more things to cover. So couple of topics we didn't quite cover. Actually, what? Sorry, let me just quickly check. Feel like this is missing a slide. Okay, well, this is whatever. We also obviously covered the PyTorch and data join stuff. That slide's kind of missing, but whatever. You learn, at least you know that we covered a lot. But there are actually more that it didn't cover. Right? In fact, if you were to like kind of balance out in terms of things I covered versus things I haven't covered, there are far more things that I haven't covered, quite obviously so actually, right? So, a couple of topics that you might come across that actually you might wish to learn would be something like exception handling or error handling. So whenever you run into errors, you get this red messages out. Sometimes, or actually oftentimes it's a bug, meaning that you probably have to just fix it. But sometimes you actually know a potential error is going to occur. Maybe you try to load the file that doesn't exist. If that happens, and if that's something within your expectation, you don't necessarily want your whole code to crash. You actually want to be able to more gracefully deal with it. That's where you can use something called exception handling, that says, try this code, and if it fails, and if it's among the failures expect, do something and continue with the code. It's not the most typical thing you need, but as you do more and more complex stuff, especially with stuff that it's outside of your control, like network access or file access, you do have usage for something like exception handling. Another thing we didn't quite cover would be debugging your code. There's a reason I didn't cover is that oftentimes debugging your code comes from just reading your own code and trying different things out and putting print statements in, and that's how you debug your code. And there's a lot of school of thoughts as to like whether you should really learn to use specialized debugging tool, or you should just really learn to use this plain old debugging technique of printing out your values. Practically speaking, I subscribe to like, well, if you can figure out by reading your code, that's a better learning experience anyway. So minimally speaking, you want to be able to do that. But there are definitely cases where something like debugger, where it lets you step through line at a time and test it locally to see exactly where the error comes from, could be very handy in debugging very sophisticated issues. Another thing I didn't quite cover is something like context managers. It came up once in the whole workshop. It's this thing that starts with something something statement, and that's called context manager. I totally glossed over it. Another one is this at syntax. I'm not talking about the matrix multiplication at, but for example, in today, when they actually did the data join, there's an at schema at the top. That's something called a decorator. It's a special Python syntax to add additional features to your classes or even functions. A bit advanced, but I didn't cover, but it's not that difficult. In-depth object-oriented programming pattern was also not quite covered. We talked about objects, we talked about instances and classes, and even inheritance, but there are even more to this. There are something like instance and static properties, class properties, getters and setters, and even multiple inheritances. And yet more, there are many, many, many more Python packages that we simply never visited. We maybe looked at something like time. We might have looked at maybe like get pass we looked at, but there are like literally hundreds, if not thousands of packages out there that already comes with the Python. And if you start talking about packages, you can just go install with pip install or conda install. There are literally millions of packages out there. So there's no way I would have covered them all. But the baseline being that you should not try to learn them all at once. There's really not ever a point to try to learn all of them at once. So one thing to keep in mind is the learning programming is really like learning any other skills. So for example, pick guitar or dancing or whatever you imagine. It's not something you're just going to go and learn and be an expert in like 3 months, right? If you can do that, good for you. But good majority wouldn't be able to do that, and it's just not going to be a right expectation to have for yourself or to anyone else who's learning how to program. This is something you build over lengthy but continuous times spent and practice in it. So with that, I do want to give you a bit of like mentality thing to go along with learning how to program. If you're already a programming expert, you can ignore me. Maybe you can already tell me, you can tell me otherwise what is the right mentality for me to have, because I will still consider myself learning how to program. So my guide on how to learn to program, first of all, is that if you can really explain to someone how to go to the nearest grocery store and give enough clear instructions, you know how to program, or you can program. So let's get that out of the way. People can't program, okay? With logic that you're exercising on day-to-day basis, definitely like working in research environment, yes, you are capable of programming. So if that's ever a doubt in you, get that out of your system. The question becomes not so much can I program. The question is how do I get to the point where I can program to get what I want. So one key advice is read other people's code. If you have a friend or coworker who writes code for you, maybe there's already code exists in your lab that does a lot of processing, that's a great opportunity. Try to go read for it. If there's someone who knows the code better than you are, great, go ask them whenever you get stuck understanding the code. Reading other people's code is a great opportunity to learn resources and packages you've never seen before. By looking them up, you get to learn new packages and new tricks in the code. And just in general, very good way to enrich your code reading skills. By reading more codes, good and bad actually. Reading bad code could be almost as helpful as reading good code. You first of all understand how terrible that code is. You probably would not write it like that. And if you can answer why is this so bad, that allows you to really understand something about how a code should be written. At least how a code that you could easily understand and hopefully work could be written by avoiding bad examples. Okay, this should go without saying, but I must say, you should write code. Reading others' code and staring and reading a bunch of books is not going to make you a good coder. It's like just because you go to a museum and like look at endless number of paintings doesn't make you a painter. You have to paint. You have to write. But that being said, it's far more important, I will emphasize, it's far more important that you write more often than you write as much code. One day you write 10,000 lines of code and you stop for 1 year, you're a worse programmer than a person who writes 10 lines of code every day. Okay? It's the repetition, it's the continual exercise that really makes you better as a coder. And besides, oftentimes we argue for how shorter lines of code are better. So if you really tell, like, I've written like 10 million lines of code, people are not going to really appreciate that. All right? So other thing is that if possible, and this kind of goes along with reading other people's code, but if possible, and you should try to seek this, have other people review your code. And this doesn't have to be an expert. It could be just your peers. If you're learning to code together, just have the other person read your code and give some comments. They don't have to give a deep and insightful comments. They just could tell you, like, I didn't understand this portion of the code. Like, I would have written it like this. Things like that will tell you how you probably could change how to write. And this also gives you a great opportunity to also read someone else's code. Right, and another thing is, like, this again goes along with a lot of stuff. Learn a new package and feature as you encounter them. That's one. This happens often by reading other people's code, or as you find a necessity for a package. Like, you start implementing something, like maybe what you start to implement is a mechanism by which you invert an image. Rather than going and spending all the time inverting an image yourself, maybe you should ask, maybe someone has already done this. Can I just Google it online? So Google is your best friend and a great teacher when it comes to things like this. Just Google it, see if it already exists out there. That's your great opportunity to learn how to code. But again, if you get a package like this, try to read it. Like, if you're just going to be this blind person who copies and pastes codes from online, you're not a coder, you're a copy and paster. All right, and this actually goes not for coding alone, but for everything in life, in my opinion, especially for computational stuff. Predict. Like, try to think and predict what's going to happen next before you do it. It goes for coding, goes for any experiments, goes for any analysis you're going to perform. Make prediction. See if you're right. If you're wrong, figure out why you're wrong. This is one of the best ways to learn. All right? If you just blindly follow through and run code and just accept whatever comes out, you're not going to be as critical of a code writer or reader. And this goes for any experimental analysis. Just don't take in just because it came out. Like, see if you agree or disagree. And that's really the best learning opportunity for you. All right, finally, and because I've been kind of giving you a bit of harsh points, perhaps, do look back at your code once in a while. Look back at the code you wrote like 3 months ago, 6 months ago, even a year ago, and see how would you write your code now. Do you still understand your code? Maybe you actually know how to write it much better. Maybe you actually laugh at your code thinking like, oh, I'm taking like 20 lines there. I could write this in 1 line. That's an improvement. It's a great chance to appreciate how much you've learned. And if you feel like you've learned a lot, that should give you confidence you'll probably be learning more in the coming months and coming year. So just something to keep in mind. All right, so just to wrap things up, I will keep the Edgar's Guide Slack group open. I mean, it wasn't just meant to be for this alone. So if you have any questions for me, just feel free to ask. I'm not going to guarantee you're going to get like extremely within 1 second response or anything like that. But once in a while, I do come along and just read it. I mean, at least it makes a ping on my phone all the time, and I tend to respond to these things pretty quickly. And also just take that as an opportunity to like talk amongst yourself, right? Just create channels. You're all free to create additional channels. Talk about stuff. I might drop in, or you might just not need me. All you might need is just other people also learning the same thing. All this workshop material, including the Python code or the notebooks, text code, as well as the slides. So far, slide hasn't been included, but all the slides and obviously the videos, they will all be made publicly available. And the videos will also be made publicly available. We got permissions for that. Still working on the exact details, but this could be shared completely. So could be a great resource for you to review. Or if you have a friend who wants to learn Python and they couldn't find any better resource, then at least they have something to look at. All right, and all previous workshop information and any upcoming information about any workshops, right? I'm not going to always be here. I'll probably be in Germany or I'll probably be in other places. But I tend to give workshops. That's kind of something I do because, yeah, it's a weird hobby I have. So I give a bunch of workshops. I teach a lot of stuff, and I will try to share this with people. When I have it recorded, or at least if I have notebooks along with it, now I'm going to have a place I can post. So, at least there's one place where there's a bunch of notes with this one guy who's teaching something, right? And I hope to provide additional posts and videos for even the stuff that we covered, or maybe additional coverage material for you to look at. And not just Python programming or scientific computation in Python, but just programming and computer science and actually computation in general. Something I like to cover in general anyway, so I'll try to have videos and maybe materials as it comes along. So that's technically the end of the workshop. So with that, of course, the last person to thank is all of you. Because if it wasn't for the fact you actually cared to attend, I don't have a workshop to teach. So at least you bear with me 16 hours. At least some of you attended all 16 hours. I know I forced to attend, and a good number attended 16 hours. So thank you, and I hope that you enjoyed this as much as I enjoyed teaching it. That's all I have.